Welcome to Learn Data. It's great to have you on this channel. I'm Nilesh, and in this video, we'll continue our discussion on distances. And in this last third video, we'll look at the Boolean valued vector spaces, so Boolean distances, and also an example of a user defined distance. So there's some notation that we'll look at first. Uh, so in this case, let's assume that on the bottom left we have this array, and we are trying to find the distance from the first row to the second row. So the first row could represent maybe a word, and second row could represent a different word, and we are trying to find the different types of distances, and each number, so 1 represents true and 0 represents false for some conditions. And same thing here. So if we have these n, ntt, ntf, nft, nff, so we look at what all these mean. Now for the n, which is number of dimensions, it is just simply the number of columns that we have here. So 1 2 3 4, so number of items in each of the rows. So that's why the value of n is equal to 4. Next, ntt is the number of dimensions in which both values are true. So here we have a value, both values are true. So if we substitute the ones and zeros with true and false, you can see that there is only one column that has both values that are true. So that's 1 here, and therefore the value for entity is 1. Similarly, if we look at ntf, so first value is true and second value is false. So here we have first value is true, second value is false. So we have 1, and all others are different. So we just put a 0. And so when we add all these up, we have value of 1 for ntf. And so on for nft, the first value should be false and the second value should be true. So we have f. So we have f here, false and true, and others are not false, true. So we put a 0, and so we have count for false, true arrangements in that data is just 1. So we have value of nft as 1. And finally, if both values are false, so we have this case where both values are false. So we have 1 count for that, and then others are not false, so we just put a 0. So the total count for number of dimensions in which both values are false is 1. So we'll use this notation in all the slides in this video. The very first distance is called the Jaccard distance, and it is given by this relation that's shown here in blue and also written down here. So using the same method that we saw in the previous slides, to calculate the ntf, which is the first value is true, second value is false, between a and b, we see that it is 1. So there is true and then false, so that's there. All others are different combinations, so we put a 1 there. And for nft, let's find out how many are there. So first value is false, second value is true, so we have 1 count there, and then others are different, so we put a 1 there. And similarly for the denominator, we have this additional trues, and here we can see that this particular case we have true 1 for here and 1 here, and so we have total of 3. So our total, so we have numerator total of 2, denominator total of 3, and when we divide those, we get 0.667, which is the Jaccard distance between a, in this particular a, and the second row, which is b. And down here on the bottom left, we have the code for that. So if in the get metric, we need to specify Jaccard as shown here, and here x, this is a sample array that is shown up top, and when you run the dist dot pairwise x, get this output that's shown on the bottom right hand corner, where we can see the distance from A to B in the magenta box is 0.667. And similar to this Jaccard distance, we can also calculate this distance for between A and C. So for A and C, now let's look at this. For NTF, so first true and second false, we do not have any combination which is this, so we just put a 0 there. Then first false and second true. Here we see that first is false, second is true, and so that's the only one occurrence, so we put a 1 there. And similarly for denominator, we have the same numerator plus NTT, so both are true. So we have this is true, this is true, so 1. Then we also have this one is true and this one is true, so there are 2 instances. And so we have total count is 2 here. When we add and divide all these, we get a distance of 0.333, and that's what we see here in the magenta box. So distance of A from A to C is 0.333. Now let's look at another example where we are trying to calculate the Jaccard distance between two words, mango and apple. And as we had seen in one of the previous videos, we can convert the word mango into a binary array as shown here in the top row, and the word apple into a binary array as shown in the bottom row right here. And the green check marks here show that the values in each of those rows are not the same. For example, here we have 1 in the top row and 0 in the bottom row. So that's what these check marks are saying. Now if we calculate the Jaccard distance using this relation here, for NTF we are trying to calculate number of dimensions or number of columns where we have the first value is true and the second value is false. We can see here that we are looking for 1 in the top row and 0 in the bottom row. So if you count all those here, you get 10 such columns. Similarly, if you are trying to calculate the columns where the first value is false, second value is true, so 0 and 1, such as here we have 0 in the top row, 1 in the bottom row, then you count them and add them up, we get 3 such columns. And finally for NTT, so both the columns have 1, so here we have 1 in the top row and the 1 in the bottom row, and so we have 14 such columns. So when we add and divide all these, we get a number of 0.4815, and that is the Jaccard distance between the word mango and apple. And here is the code to calculate the same. And on the right hand side we can see the output of this code, which is a pairwise matrix. And here we can see the first row and column represent mango, second row represents tango, values for tango, third represents values for apple. So for mango, if we compare it with apple shown here in the magenta box, we get a value of 0.4815 and 4818, so rounding that off to 5. And similar to this, we can also calculate the distance between mango and tango, and here we get a distance of 0.12 as shown here in the magenta square. So as we can see that the word mango and tango have only one character that is different, all others are same, and therefore the distance between these two words is smaller as compared to mango and apple, where the characters in those two words are much different. Next, let's look at matching distance. In matching distance is given by this relation shown here, where we are dividing by n, that is a number of records, rather than looking at ones and 0 count. So in the previous case we had NTF plus NFT in the numerator, that's the same here. Now only the denominator here is different. So in case of this array that we have, if we calculate for A and B, if we look at the first value is true and second value is false, so we have 1 and 0, so we have 1 count of that. And for false true, we have again 1 count for that. And then the total number of columns we have is 4, 1, 2, 3 and 4, and so we have 4 in the denominator. So when we calculate that, we get a distance or matching distance of 0.5. And so this is the code that gives the matching distance, and here is the output on the bottom right in this matrix. So the first row, second column, we see that in the magenta box that the distance between A and B is 0.5. Similar to this, there is a dice distance, and it is given by this relation shown here. again, the method is same. I want to count each of these values for the combinations of ones and zeros, put them in the relation, and then get the final calculation. Here we get a value of the dice distance as 0.5, and as calculated from the code shown here, and the output matrix on the bottom right, we see in the magenta box that the dice distance between the between A and B is 0.5. Now, similar to this, there is another distance which is Kulsinski distance, and in this distance, similar to the previous distance, here we had NTF plus NFT in the numerator. We have that one. We then have these additional terms here, and we are also subtracting all the true values. So if there is a match between both of these, then we are subtracting this. And again, when you count all these and add them up and find the distance, you get a distance of 0.833. And similarly, the output of the code in the bottom right, we can see in the magenta box, we have distance of 0.833. One new notation here, NNEQ is given by NTF plus NFT, and again in future slides we'll see NNZ, which is NTF plus NFT plus NTT. So combinations of those number of non-zero dimensions. Next, let's look at Rogers-Tanimoto distance, and this is given by the relation shown here, where again, as seen in previous video, the denominator, previous slide, here the denominator is the same, except now in numerator we are multiplying here by 2 for this. So there should be a these two should be in parentheses as shown here. So we are multiplying 2 by 2 for the summed values in this parenthesis, and then these values in the denominator. So the Rogers-Tanimoto distance that we get in this case is D is equal to 0.6667, and that is also shown here in the output of the code in bottom right by the magenta box. So for A, between A and B is 0.6, and between A and C this distance is 0.4. And moving on, there is a RussellRao distance, and here we can see the distance. Again, this is the relation for that. We are dividing the number of non-zero dimensions by n, and here we get a distance of RussellRao distance of 0.75. And here in the output for the distance between A and B, we have 0.75. Distance from A and C is 0.5. Next, there is a SokalMichener distance, and this distance looks similar to the Rogers-Tanimoto distance. And here again, when we plug in the values, we get a distance of 0.667, and that's what we see here in the output matrix, where the distance between A and B is 0.6667, and the distance between A and C is 0.4. Next, let's look at the SokalSneath distance, and here again, this is the relation for calculating the values, and when we plug in the values, we get a distance of 0.8, and that's also seen here in the output from the code, where we have the distance between A and B is 0.8, and the distance between A and C is 0.5. Now, probably wondering why there are so many types of distances and when they are used or why they are used. So one of the examples that I can talk about is, let's say if you have two different data sets, and if you're trying to find the similarity or dissimilarity between those two sets, depending on how big or small the differences are between those two data sets, these values could help gauging this particular similarity or dissimilarity between those two. let's say for example, in one of the if you have two images, one image has mostly values of 255, and there are maybe 10% values that are less than 50. Other image also is image of a completely different object, but then it also has majority of the values 255, and 10% of the values are for the actual object. Now if the overwhelming majority are similar pixels, so that could mislead into saying that those two images are the same. However, using one of these differences which can negate some of those background similarities in the background of the images, we could get a better estimate of how those two images are related. Are they similar or different? I'm not sure if that confused you more or that helped you understand what I was trying to say. But we'll look at a couple examples as we walk through in future videos to see how some of these are implemented. And finally, let's look at a custom function that we can use to calculate the distance. Such a function needs to satisfy these 4 conditions that are shown. One is that the distance has to be positive, and that it can be 0 only if the points are coincident, and then the distance measured either way should be same, so either from y to x or x to y. And then the triangle inequality, that is the distance of one side should be less than or equal to the sum of distances from the other two sides, and that's what is shown here. And the code is written on the bottom left, where we see in yellow new dist. That's the function that calculates the Euclidean distance and returns it. And to call that function, we can, within the distance metric dot get underscore metric, we need to specify the string PyFunc, and then specify the name of the function. Func is equal to new dist, and then call the dist.pairwise x, and you get the output that is shown here on the bottom right hand side, where we have the distance between the points x and y as 3.6056, as we had calculated earlier in one of the previous videos using Euclidean distance. That was it for this video, and this also completes the 3-video series on the distances, different types of distances. I hope in this series you got an intuition about what these distances are, how they can be calculated, and also how we can compare different distances. So for the same set of data points, we can get varying value for the distances based on what criteria we use to calculate the distance. And also finally we looked at a custom function. So if you have a custom way of calculating a distance, so you can write that up in a function and call that using the distance metric method. If you have any comments or suggestions, please let me know in the comment section below. In the next video, we'll look at nearest neighbors and see how some of these distances would be used in those methods. Until then, please like, share, and subscribe. Thank you.